Okay, challenge. Do you think this effect can be created in Flutter today running at 60 frames per second? And how would you approach it? It's not just drawing a circle, it's actually drawing circles that kind of merge together. And what we want to do is create this effect in Flutter and make it run at 60 frames per second. And we'll do that. So I was inspired by Matthew Carroll with his channel SuperDeclarative, where he created exactly this effect in Flutter using his package Flutter processing, where he was inspired by the coding train. Here the coding challenge was Metaballs, and I wanted to tackle the challenge as well, and especially if we take a look at what Matt has to say about it.
First, it is a really cool effect. You can see these blobs kind of morph together. The second reality is that we have a super low frame rate.
Did you catch that? He said that he has a super low frame rate. And that really caught my attention because I thought, okay, I think I can create this effect at 60 FPS in Flutter today at any resolution we want. And if you pay attention to what he has to say at the end of his video,
I wish we could get this in a shader because then we could probably get full 30 to 60 frames per second with this effect.
He's saying with the shader, you could get 30 to 60 frames per second with this effect. And I agree. This looks like it should be put in a shader and that would just be awesome. And I'll get back to that at the end of this video, which is also why this is in the title. But first, let's take a look at how I would tackle this effect, which Matt was not able to run at 60 frames per second with his processing approach to implement these metaballs, right? This is just a 2D version of this. You can look into this if you're interested. We'll just look into the practical side of actually doing it. What I will be using for it is a very bare bones Flutter project. So as you can see, we have a very simple app where we only have a material app, a scaffold, and then a so-called funvis container where we put a simple funvis. What is funvis? Funvis is a very simple abstraction on top of custom paint to give you a canvas that draws based on time. And that's a package that I created to basically create many of these animations. If you've been following me, you have seen these. I have created all of these using my funvis package, and I decided to also use this package for implementing this effect because I just prefer to use my package. If you check out the GitHub repo, you can actually find the source code for every single of these animations that I posted. And here you can see I have already created quite a few animations so far. And this one is also in the repo. You can find the source code in the description. So if you want to play with it, you can do that. So how do we tackle this challenge, right? How do we implement this canvas? How do we draw this? How do we approach it? I think the first thing we want to do is paint a background. So there we go. Challenge accepted, and we have a black background. The way we draw this black background is by, first of all, I want a fixed size. In my case, it's 750 by 750. This is actually not the real resolution. The resolution is even bigger than this. But this function from Funvis basically allows you to scale the canvas in a way where 750 is the dimension you'll be working with. It's actually not that important here, but I like to do it because it makes exporting these easier. And then we just draw the black background. So how do we proceed? I want to make sure that I use the same code that Matt used for the basic logic and only change the way we implement the actual drawing of the metaballs. So what we can do is check out the code that Matt posted in his repo, the Flutter processing repo. You can see 28 metaballs, that's the source code for that. And here you can also see all of the drawing code. But I want to obviously do the drawing differently, so the only thing we'll take from here is the blob class, which has an offset, a radius, and some movement logic, and then some paint logic. I will remove the paint logic and the radius because I do it differently in my version. So let's just copy over the blob class here. And to be clear here, what we have in the funvis is access to the canvas via C, and this function U is called every single frame. So basically we have the size and the canvas, and we can work with this in funvis, which is the same as every other canvas-based code in Flutter, which is also the basis for the Flutter processing library. So the way Matt approached this is the same way that Dan from the Coding Crane approached this, which was calculating the distance from the blobs for every single pixel on screen and then setting the brightness for each of these individually. And this is what's causing the lag. So I want to do it differently, but let's first get the setup right. So let's get these blobs initialized so that we can see something on the screen. What we do here is the same that Matt also did. We have a blob count and a blob speed. I just copied these settings from his code, and then we also want to have some blobs. I will initialize them in the draw function because that's easiest. I could also do it in the constructor or anywhere else, and I'll only do it when they're empty, so we only do it once. And then we make sure that for the blob count, so just a simple for loop, looping through the blob count, we want to add a blob and we want to randomize it. So we just use a random object with some random seed, 4269. And then we add a blob in this loop, and then we randomize the initial offset and we randomize the initial velocity. Here we can just use the offset from direction, which basically does the sine cosine logic for us to define this offset based on the distance, which is the blob speed, and then direct this distance from the zero offset to do this logic for us so we have some nice velocity. And all the bouncing logic is implemented already by Matt in the move function. So now one thing we need to do, which he also did, was we need to make sure that the blobs move. So we need to call blob.move. Let's quickly do that. Here we go. And now we want to also paint them. So let's just do circles for now. We loop through the blobs again and paint a simple circle using the canvas at the blob offset, which we get from the class, then with some radius 50, for example, and then with the paint, which we just set a white color. So let's take a look at what that looks like. There we go. Now we have some white blobs moving around. And if you've watched Matt's video, you will kind of recognize this because this is basically the same as his, because we are using his code for the movement, which is the whole idea, right? The challenge is doing what Matt did, but having it run at 60 FPS. How do I approach this now, right? Because I obviously can't do the same as Matt, because then it will lag and not be 60 FPS, but we want 60 FPS, we want the bigger resolution. We kind of need to find a different way to do this. And when I looked at this, I kind of thought, okay, is there maybe something that we can use in Flutter to do this? And obviously when I looked at this, I immediately thought, yes, for sure, 100%, I can do this at 60 FPS. And two things came to my mind. First thing, blend modes. It reminded me a lot of when I did After Effects, for example, where quite some time ago, actually, in After Effects, I created this Metaballs effect without even knowing what it was, and I just used blend modes and stuff like this, and that's why I kind of knew, okay, this has to be possible with a different approach at 60 FPS easily. And blend modes, for sure, I knew, okay, we need some kind of adding together these circles. And then the second thing we need is some way to make these circles like fade out, because otherwise we just have this, right? Like these have hard edges. And how do we avoid these hard edges? Well, obviously by creating gradients, right? So let's get rid of the hard edges and use a gradient instead. Here we use a radial gradient. If you haven't seen this syntax, this is from Dart.UI. There are two in the Flutter framework. There's also another gradient abstraction, but we're using this one directly. What we can do is, again, pass the blob offset, some radius, again 50, and colors. And what we do here is we fade from white full opacity in the center to white zero opacity to the outside. So basically what we want to have and what we will have here is the same as this, just fading out from the center. So let's draw this. The way we can do it is using a paint object and applying this as a shader. This is already the keyword, right? Why is this more optimized? Well, because these kinds of gradients in Flutter are actually considered shaders. And this means that on the paint object, we can do canvas, draw paint, and apply a shader. And these shaders are basically the only ones supported right now, I think, are the image shaders, like color filter and these gradients. So there we go. We have now the fade out effect from the center, but obviously we are still very far away from this effect, which we want to have. Like, we don't have any of the glow, nothing. So let's bring in blend modes, because that's what we're looking for, right? That's what I said, what I had in mind. And if we take a look at the blend modes here, actually, there are quite many. And how do you know which ones to use? There are actually not that many. And if you're somewhat familiar with blend modes, you will see these kinds of families of blend modes, like the color blend modes, then the destination and source blend modes. And you know, all of these can't be it, right? What you might think is something like screen, but the one I remember from After Effects was the add blend mode, which is plus in this case. It's the closest one. And what plus does here is it will basically add together the colors. So if we reload this, we can see already, okay, when these circles pass, they seem to kind of add together and do this kind of effect already. What we can now do is increase the radius and make it more obvious. And now we're already pretty close. I think at this point, it should be obvious to anyone, okay, we will be able to pull this off, because this is already very close. Maybe it's still not immediately obvious to you how we pull off the rest. So let's point out the problems here. We have these hard edges still, like you see these kinds of lines, right? These lines are going through the circles and it looks really weird. And then the whole background is black. If you look at what we want to have, it's kind of everything is glowing. We still need to do a bit. And the first thing I want to get rid of is these black lines. Experimenting with this, we can't really get rid of them when the shader ends, because it will always have this hard edge, because it's still a circle. So what we would need to do is make sure that the circle is so big that we can't see the edge at all. So what we could think is we take the size, and for example here it's half of the size. Let's see what this does. Okay, it's kind of still the same, so let's just take the full size. And here longest side is just, we have a size object, right, which is returned from this function as I said earlier. And this will just be 750. And now if we take a look, okay, everything is white. But you will sometimes see small glimpses of what we're looking at the edges. And then you know, okay, this is actually, there you can see it. This is actually what we're looking for, right? These small glimpses of, okay, everything is glowing, it's just glowing very bright, and that's why you can't see anything. So now the question is, how do we control this? Because we're still super far away, and we need some way to emulate what the distance code here does, right? This code, it always computes the distance, and then it sums it up. And how do we emulate this? If we just have simple gradients that fade from one color to another, then we'll never be able to have this effect, because it doesn't factor in that the further something gets away, the faster it gets darker, right? So we need to have this kind of squaring effect, where the further it gets away, the farther it gets away, the faster it gets darker. So we need to have some kind of squaring, but the first thing we need to do is we need more control. And what we can do here is, if we look at the constructor, we actually have access to color stops and more colors. So let's first try to get access to that. If you look at the default color stops are actually 0 and 1. What this means is that the full white starts at 0, like at 0%, and the completely transparent, it ends at 1 or 100%. If you have multiple colors, you can use these color stops to basically define like how much of the 100% where one color should be. An example of this might be we create another color that has low opacity, for example here, and then we make sure that at 10% this color is already reached. And then the last 90% is faded from this color to the fully transparent color. And then if we reload this, you can already see, okay, now we're getting closer. Maybe you disagree, but you can see, okay, from like 0 to 10%, we're fading to this somewhat transparent color. And then from 10% to 100%, we are fading to fully transparent. And that's why we're now somewhat closer, even though it obviously still looks horrible. Now it's also very grainy and we kind of still have the same artifacts as before. So not a huge improvement. So my thought was, okay, like how far can we take this, right? How far can we take this? How many colors can we put into this to make it a smooth transition and to fully control when which color is applied? And I just tested it out. And what we need to do for this is obviously do it programmatically, because we're not going to write all of the colors manually and all of the stops. So what we want to do is basically store some kinds of like a colors list and a stops list. So let's make sure to create these lists. And then what we also need is to define like how many colors and stops do we have. So I call this the shader resolution here. And don't worry about the value right now. I will explain it at the end, why I chose this value. It's just like, remember, it's a very large value. This is above 8,000. So now we are using more than 8,000 colors to completely control how it looks. So let's initialize these in the same way that we also initialize the blobs. So make sure they're empty, and then we can also say, okay, if the colors are empty, we also want to initialize the stops. So let's like assert that this is actually the case, and then add all the colors. So for every single color in the shader resolution, like for every single step, if we have 8,000 steps, we loop from 0 to 8,000, or in this case, we loop from 8,000 to 0, because what we want to make sure is that the colors go from fully opaque to fully transparent. So from fully white to fully transparent. And that's why I started with the highest I first. And then what we can just do is this would be white, right? Like all on the full. This is like 256 for the RGB. And now we do the opacity, which is then just the I value over the shader resolution. So this will just go from 0 to 1, or in this case from 1 to 0, because we want to go from fully white to fully transparent. Do the same for the stops, but the stops, remember, they go the other way around. So they go from 0 to 8,000 in this case, roughly, right? From 0 to 1. So again, we do I over 8,000, then it would be 0 to 1. And now if we reload this, you can see it's fully white again. So we are at exactly what we had before without the color stops. So now we're exactly again fading from fully white to fully transparent, just from 1 to 0 linearly. What I said is we want to have the distance in here, right? We want to have this concept of distance, where if you look at the video, you can see, okay, the closer they get together, the more they merge. So we need to have this concept of the farther it gets away, the faster it gets darker. And the way we do this is by making sure that, in this case, the higher the I values are. So the closer the I values are to the center, this is what we do by squaring, because imagine we have 8,000 by 8,000. That will create a huge I value, but as we go lower towards the outside, so towards 0, then it will have less of an impact. So we will have way greater values at the center, and then they will fade out, right? So this is what we do by squaring I. We just square it. But now we need to make sure that it's still from 1 to 0. So if we square this, we also need to square the shader resolution like this, right? So now we squared the I and also square the shader resolution. This might look very weird to you. Why are we doing I times I over shader resolution over shader resolution? We can also write this simpler by just having the original and then like taking the second power, which is squaring. So now we have, again, I over shader resolution, and we square it. This is the same as what I had just written, but it might be more intuitive to you. Maybe, maybe not. And then we want to do the same for the stops. In this case, the stops actually don't mean anything, so we don't want to modify the stops at all, but we need to make sure that the stops match up with our colors. This will have some importance in a second, but we don't do different stops. So we only align the stops exactly with the colors. Obviously, it's again reverse. This one goes from 0 to 1 instead of 1 to 0, but it's the same. We are just squaring as well. So let's reload this and see what happens. And see what this does. This is already basically it. And that's just super amazing, I think, because it shows, okay, you can really control these gradients. If you just think about it a little bit, you can control them to exactly your needs. So now we have the gradient that's really is very bright in the center and then is fading out very quickly. So that's what the squaring does. And now you could say we're done, but obviously in this case I'm not satisfied, because if we look at what we're trying to do, which this looks very close to Matt's implementation. I actually asked him, do you think this looks the same? And he said, yeah, it looks the same to me. So let's use this as a reference. And as you can see, the balls, they look way bigger, right? The blobs, they look way bigger when they don't touch anything. And here they're just like tiny points, which really sucks because we want this to match more. So how do we go about this? Now it's like getting somewhat mathy, but I didn't want to really make this any complicated. So let's think about it. In this case, what would you usually do? You would usually apply easing, right? Like, easy ease, where you ease an animation where you don't want to go linearly, but you want to make sure that it like goes slower at the start. The same thing we want here. We want to make sure that right around the ball center, this whole squaring goes slower than to the outside. And the way you do this is using easing. And in easing, what we often use are cubics. If you're not aware, there is this concept called Bézier curve, and it's basically a curve where you have a start and end point and some control points that pull the curve in some way. This is, if you look at this, I really like this. This is also how you would draw a curve with a canvas, right? You would define a start point, an end point, and then you would have some control points that pull out this curve to create this shape. And we can use the same concept of a cubic in this case. A cubic Bézier curve is essentially a curve that has two control points and one start and end point, and that's the cubic. The quadratic has only like one extra control point, and so on. And the cubic Bézier curve is what's used for animation easing. So if you take a look at this, here we can compare a linear animation with some eased animation. And this is just a tool to visualize it, because I'm sure that not everyone can visualize this in their heads. And what we want is, we want to have slowed down at the start, but very quick at the end. So we take this end thing and we make sure, okay, here at the end it goes very quick, basically like instantly, right? This is instant. And this is the very simple Bézier curve I used. So I actually didn't use this tool to approach it, but if you have some kind of intuition for Bézier curves, it made sense to me why this works. So I just took it and it looked pretty good. So let's try it out. Let's apply it. So here we have a cubic. This is also a concept in Dart, or basically in the Flutter framework, the animation curves.dart. we can just create a cubic, the 1101, which is this very simple cubic I just described, or the very extreme one. And then we transform this squaring, right? We just transform it using this cubic. So we basically ease the color transition. And let's take a look at how this looks. Okay, this is what it looks like. And this is the effect. This is exactly what you saw. This is running at 60 frames per second, possibly even more. This is a very high resolution. I mean, compared to the 400 by 400 that we saw in the Flutter processing example. And it's super smooth, and it's the effect, right? And it's very simple, right? I basically put this together in 10 minutes of playing around with it, and this is what I got. I didn't try to like alter it and try to improve it, but I'm sure you can improve it. So again, the source code is linked in the description, and if you want to play with this, just go ahead. So there we go. Challenge completed. We did it. Yay, we have it running at 60 frames per second or even more. And actually, I also have this running as a web demo. If you go to funvis.creativemabino.dev #30, you can see it running as a live demo on Flutter Web, exactly this code. If you don't know this demo, it's just basically, if you go to the repo, you can take a look here at the demo app, which is running live. I think in Chrome it performs way better. And here I also have all the other ones, but here you can just take a look at this, the 30, and it's running very smooth for me, very smoothly. So that's very nice. So easily 60 FPS. And remember, this was in debug mode. So it's like kind of proof for, okay, this is definitely running smoothly. And the reason for that is definitely that we're using the shader, right? We're using the radial gradient. Then let's take a look at the one thing I mentioned that I didn't explain. And this is, how did I come up with the shader resolution? Let's actually take a look into this. So here I have some comments that explain this, but let's first look into what would happen if we had a smaller shader resolution. So let's, for example, try 10. Okay, so this is what it looks like. It still works, but you can see it's very blurry. And this is if we only have 10 steps, obviously, we don't have that much precision. And this is why it's, as I said, like very blurry. We can go down to 2, then we have the same effect as before. So this is like kind of from the start, but a bit better actually, because we have this easing applied, right, with the cubics. But the question for me was like, how far can we go? If I go to 500, it looks a bit better, but to me it kind of looked really grainy. I don't really know where this artifact is coming from. It's probably because of the internal gradient implementation. And then I tried to push it, and what I noticed is if I do, for example, 9000, it doesn't work at all anymore. And then I was like, okay, why is this? And I go back to 8K, and suddenly it works again. And this was really odd to me. And what I figured out was that 8191 entries in the colors parameter, so basically passing 8191 values here, is the maximum number of values that you can pass before it goes completely haywire. So if I do 8910 here, you can see it doesn't work because it's 8190. It works, but if I do 8191, it suddenly doesn't work anymore. And then we can just take a look at the hex representation. This was 01 FFE, and the reason it's actually in this case 8190 is because here we're actually adding 1, right? We're adding 1 more than there actually are, because we're starting here. I could have also subtracted 1 here, then it would actually be 0x1 FFF. And this is what it looks like. And then the 8192 in hex is 2000 and or 2000. And if we look at it in decimal, it kind of becomes clearer that here, okay, we have like the bits, and then these bits might be the only ones accepted in the shader, in the gradient. I don't know. It's definitely something to do with that. I would say probably just to do with the internal implementation, but I don't know exactly why these values. Maybe it's arbitrary, maybe it has a deeper reason. Who knows? I know that it's smooth. Passing 8,190 is smooth, so we can do it, and it's the highest value we can do. And talking about shaders, let's get into that. I used shaders arguably to implement this, and this is kind of why we need shaders, right? Because we want to implement effects like these and maybe even more complex effects that don't work with some kind of workaround that I found where I'm really creative with, like, I know, okay, we have blend modes, I know, okay, we have these kinds of things in Flutter, and then I can imagine how to do it, whereas someone else like doesn't see the hack immediately. Then what we really want to have is shaders, because then we can do it properly. Then we could actually use the implementation that's proposed in this video and run it efficiently if we have access to a shader. So actually in the Android 12 beta, we can see that there is a new overscroll effect. If you remember how Android did overscrolling previously, it was always this glow. But now they have a new effect, and you can see the stretching. And apparently, this stretching is such a complex effect that you can't do it with what Flutter provides today. And the reason for that is that this stretching is not uniform. So, like, the further you get to the top, the more stretching occurs. And this is not currently possible in Flutter because there's no such implementation using the transforms, which means that we need to write a custom shader to make this work. And this is why there's also currently work on Flutter to add shader support. So here you can see the issue to add this behavior. And there we can see, okay, it's being tackled, and we're looking into a shader project. So the fragment shader API is being added to the engine in order to support us writing custom shaders and working with this, which is like super cool, because this means we will be able to achieve effects like this or more creative effects like this challenge using shaders in Flutter. And I just wanted to share this because I think it's really cool. Here you can see the publicly shared document about the fragment shader API. Here you can see it's a very simple API on the Dart side, because obviously you don't write shaders in Dart. We will have an API to then use it in Flutter, which is pretty awesome, and this will hopefully allow us to write more awesome effects. But also, I fully support the point that Matt is making here, that we kind of want to have shaders in Flutter, and we need to have them to be able to implement these more complex effects, to be able to do these awesome things. And I'm really glad that I was able to implement this effect running very smoothly in Flutter right now, but it would be very awesome to have access to shaders to also include these in our apps. And remember, you can learn anything, creative creator maybe not, out.